Good morning to everybody. And so, as I mentioned, the linear groups is such a title. It's a very vast topic, and we touched upon a few things, and a few more things we'll touch upon today. And some of these we could discuss in detail. But at the end of when I upload the notes here, I will also point out to various directions in which you could go, and textbooks and other sources that you can look for when you want to read more about these things. That's after the talk. So let me just start with today's version. What is it? So as I mentioned, you cannot talk about linear groups without mentioning linear representations, which means representing an abstract group by means of matrices. And we already had a series of lectures by Professor Manish Kumar, I guess. I was looking at what he had done. I may not have looked at it very carefully, but I think there are something that we can say here which are slightly different from what he said, because the basic things are the same, and it's worth repeating here in some way for people who have not seen this before. Because representation theory is at the center of mathematics in many ways. Different types of representation theories. For example, if you have heard the name Lagrange program, which is like some kind of grand unification theory in mathematics, at least in number theory, if not in mathematics, then representation theory is the main player there. Okay. Anyway, so having seen how matrices are really amenable to calculations, so we representing them as matrix groups will be very useful. So instead of just saying it, okay, it can be very useful. We have to look at various concrete examples of why they are useful and how they are useful. So just mentioning some topics under which representation theory plays a big role. I mean, I'm starting with some very simple things. Dirichlet's theorem on primes in arithmetic progressions. Okay, we will not talk about it, of course, because each of these topics requires at least 15-20 minutes of, and then a particular direction. It's very specialized. So Dirichlet's theorem is that if you have two positive integers a and b, and they are relatively prime, then say a and b, then in the arithmetic progression a modulo b, that is a plus b, a plus 2b, a plus 3b, there are infinitely many prime numbers. So the proof of this is using representation theory of abelian groups, for example. Okay, and then the quantum mechanical model of the hydrogen atom. This also can be explained by the SO4 representation theory. And there are various abstract, purely group theoretic statements, like there is something called Frobenius theorem, very beautiful statement. Any finite group, number of elements satisfying x to the power n equal to identity. Okay, the number of elements they satisfying this is a multiple of GCD of n and the order of the group. Okay. Or more specifically, if d divides the order of the group, how many elements satisfy x power d equal to identity? It's a multiple of d. So amazing looking, such a simple looking statement. Of course, there are proofs now using not using representation theory also, but most naturally the proof comes from representation theory. Many other statements are there which I don't recall here. So representation theory plays a role in very basic ways. So what's the representation? Let me again recall, which you might have seen in earlier lectures. Given a group G and a field K, so often you think of R or C for just for concreteness. So many times you can think of finite field, you can think of some other periodic field, depending on your taste. Depending on what field you take, you get more and more special things about representation. The representation is simply a homomorphism from G to invertible linear transformations on an n-dimensional vector space. Okay, this finite dimension is what we are looking at always, finite dimensional representations. So, as we know that the invertible linear transformations can be identified with n by n invertible matrices by choice of a basis. So what is an obvious representation? Of course, you can just completely forget that the group is has to act on something. You just let it act really. That means the linear action of G on V is just trivial action. That means G goes to identity matrix. This is, of course, you have to take care of these things also. Because what happens is, even if you take some group and some representation into, let me have my picture also so that you can see my gestures. So even if you have a big group and a representation of that group, maybe this is very non-trivial representation, but on certain subgroup, it may be trivial. So it is important to keep track of this trivial representation also. Okay. So first example for a positive integer n, one-dimensional complex representation, the cyclic group of order n. So just send say 1 to e power 2 pi I by n. It's a group homomorphism. That means 1 plus 1 will go to e power 2 4 pi I by n, etc. So primitive nth root of unity you can send it to. So this is a homomorphism. This is a representation of dimension 1. Two-dimensional one we want into real representations. This is actually a little bit of cheating here in the sense that when you have one-dimensional complex representation, you can make it into two-dimensional real representation by means of this. What happens is you take a basis of C over R, namely 1 and I, and write this as matrices with respect to that basis, and you will get these matrices. Because e power 2 pi I r pi by n is cos 2 r pi by n plus I sin 2 r pi by n. Anyway, so this is one other example. Then we have already seen that the permutation group of n symbols on n symbols has a representation as n by n invertible matrices. Yes, as permutation matrices. So as I again and again mentioned, if you take the permutation matrix P sigma to be that for which the ith row is the sigma ith row of the identity matrix, sigma being the permutation, then when you multiply matrices, it corresponds to multiplication of permutation sigma and tau with sigma first and tau later. Okay, for instance, I mentioned here, let's look at S3. S3 has 1, 2, 1, 2, 3, and so on. So look at 1, 2, you send it to this. This is the permutation. The 1 and 2, the first and second rows have been exchanged, okay, transposed. Third, 3 is the symbol is left as it is. So that means third row remains as it is, etc. So you can see the cycle 3, 2, 1 goes to this. Then you multiply these two and you see this is the multiple. So just to check that this convention is correct, I have checked for a particular example. Okay, now look at C star. As I said, often when you have a bigger field containing a smaller field, and you have representation into a bigger field of certain dimension n, then corresponding you have representation of larger dimension over the smaller field. So a very particular case of that is C over R. So we have a representation of C star over C. What is the C star representation over C? It is simply identity inclusion. C star to GL1C isomorphism. That's what you have taken. And then you take a basis of C over R. So when you write this A plus IP into as a multiplication by A plus IB. Suppose you look at multiplication of A plus IB over C. What does it matter? What does it show? You have basis 1 comma I. So 1 goes to A plus IB, so it is A plus IB. What does I go to? I times this, which is AI minus B. Okay, minus B plus AI. So minus B plus AI. So with respect to the ordered basis 1 comma I, this is the matrix of this. In any case, so this way you can get many representations of higher dimensions when you have subfields. So this is a particular case of that. For any finite group of order n, okay, now we can construct some kind of universal object in the sense that you look at artificial vector space which is made up of, suppose the group of the order n, basis of n elements are there. You take one basis element corresponding to each group element. So just to distinguish between the group element and the basis element, we call it EG. So vector space V is abstractly vector space in these n symbols E1, E2, En, where are EG1, EG2, EGN, when G1, G2, Gn are the elements of G. Then what you can do is when your G is any element of G multiplies on the left on G, so that gives a representation of G on GLV on V. G to GLV, because what is it doing? EX is G sends EX to EGX. So this is actually a permutation representation. It is permuting the basis. So in fact, elements of G will now look like permutation matrices. Okay, and then the notion of representations being equivalent, because representation is something the group is acting by linear transformations on a vector space. Now we have, it might look like it is acting on another vector space by some other way, but in reality, since we talk about groups being isomorphic, the actions being isomorphic is same thing as saying equivalent representations. This is a definition. Take two representations alpha and beta into on vector spaces V and W, because everything is finite dimensional. Okay? We can talk about infinite dimensional representation theory, which we don't do now. But once we know finite dimensional representation well enough, then we can see what things can say about infinite dimensional, which I don't do in today's talk. So let's say alpha and beta are equivalent. Okay. So when are two vector spaces isomorphic, that we know. So V and W should be isomorphic as vector spaces, but then the representation is isomorphic simply means the action of G on V is carried over to the action of G on W by this isomorphism, which is simply one way of saying that T of alpha G is beta G of T. Meaning the isomorphism between V and W, say T, there is an isomorphism which satisfies the following property, T of G times V. What is G times V? That is alpha G acting on V. Is when you take T of V and then let G act on that. So it is commuting with the G action. G is acting on this, take the image, and on the image, how is G acting? So it is respecting the G action. So in terms of matrices, this is simply because as you can see, that is why I wrote it like this. So they are actually conjugate. So once you write same dimensional vector spaces, of course, GLV is isomorphic to GL and K. So alpha and G or beta are two homomorphisms from G to GL and K. Then these are equivalent, corresponding representations are equivalent simply means there is a basis or the invertible matrix which takes single invertible matrix, not depending on the element G. Okay? Single invertible matrix so that for every alpha G is taken to beta G by this conjugation. Okay. For example, look at, as I said, look at this again. Look at two-dimensional representation for Z mod and Z over complex numbers. This one, e power 2 pi r by n, e power minus 2 pi r pi by n. And beta is this one which I mentioned, cos and sin and minus sin and cos. They are equivalent. In fact, this matrix will conjugate this. So it's all very elementary. At the same time, it is subtle. You have to do a lot of bookkeeping. Note that if alpha is the representation, then for two different for choices of basis, two representations are equivalent. Where because when you change basis, the change of basis matrix takes one to the other, so they are equivalent. So changing basis will not affect. So now the very important way that representation is featured actually. So it's like saying if you have a class of people, then there is a, let's say, leader or a captain or something like that representing the class. Similarly, for a representation, there is something called character of the representation. Namely, representation is a homomorphism. Now, when you look at this homomorphism, then for every element, every group element G, row of G, is an invertible matrix. So whatever the matrix is, because the matrix will depend on a basis of V. However, the trace of a matrix does not depend on the basis. We know that. So without writing any basis, we can say if the row is a representation, then trace of rho G makes sense for every small g. So this is a function now. So for example, think of complex representation. V is a complex vector space. Rho is a complex representation. Then character is a function to complex numbers. Every element small g is sent to wherever the corresponding matrix in any with respect to any basis is there, look at its trace. Okay, there is a way of defining trace without going to matrices, but you don't need it really. What I'm saying is that take any basis and look at the corresponding trace, corresponding matrix and trace. We know that it does not depend on the basis because with respect to other basis, it will be conjugate matrix, and conjugate matrix is the same trace. Trace of AB, A inverse is trace of B. So there is a well-defined function called character of a representation. So this is a function. Representation is going to GLV, character of that is going to the underlying field. So think of it as a function. So as I said, trace can be computed by considering the matrix with respect to any basis. So the reason for introducing this sort of representative of this rho is just pushing that, okay, this chi rho is going to represent me. Rho is itself a representation, but I'm saying rho says that chi rho is going to represent me in the world forum. And then it says the nice thing is truly a representative, because this chi rho, what happens is representations are classified up to equivalence by their characters. In other words, rho and rho dash are equivalent representations if and only if corresponding functions chi rho and chi rho dash are equal functions. Okay, so this just made one cartoon. Today I won't show any more cartoons. Where is your colleague? Is it quite a character? So yes, sir, that character vanished without trace. You know, that character is defined as trace. Okay. Yes, so now let's the notion of sub-representation of a representation. So you have representation rho, then you have G invariant subspace of W. So rho is representation means G is acting on V, G is taking V to V. So it might take some subspace to itself. That's called the invariant subspace. In this case, restriction of the action gives a representation to GLW. So representation is irreducible if there is no invariant subspace. Okay, this is the usual notion in any kind of situation in mathematics. An action or something is irreducible. There is no smaller object on which something happens. So you cannot leave out zero. Zero is always left invariant. So only subspaces which are G invariant for V or 0 and V, then you call V as irreducible representation. For example, I think I don't have too much time to say this thing, but you think about, take the Sn, the permutation group on n symbols. It is acting on C power n, because on C power n it is permitting the basis, canonical basis. Is it irreducible? Think about it. Of course, every one-dimensional representation is irreducible because it has no choice. There is no proper subspace, first of all. Okay, irreducible means there is no proper subspace which is invariant, because 0 and V are the only ones. One-dimensional is automatically irreducible. So direct sum of representations means what? So you have you represent rho 1 is a n1 cross n1 matrix. Okay, rho 1 is represented as a n1 dimensional representation. Rho 2 is represented as n2 dimensional representation. Then you can make a representation of this dimension n1 plus n2 plus nk by just putting blocks here. So rho 1 G you will have size n1 cross n1. So here is n1 cross n1 block, n2 cross n2 block, etc. This is blocks. So this is size is n1 plus n2 plus nk cross n1 plus n2 plus nk. This matrix rho of G. So you can always, given some representation, you can make direct sum of those representations. So character of the direct sum, okay, is the sum of the characters. Just check, because what happens, as I said, this is blocks, no? So trace adds up here. Remember, rho 1 G is a block here. So trace of rho G will be the diagonal entries of this. But that means diagonal entries of this you are adding, rho 1 G, and then diagonals of rho 2 G you are adding, etc. etc. So character of the direct sum is the sum of the characters. That is why you form. So you want to form a representation. Okay, if you have finite many representations, you want to form a new representation so that character of the new representation is sum of the characters of the original representation. Then this is the one, direct sum. So representation is said to be. So since you presumably have heard all these names during previous talks, and maybe you already know it also, so I'm just going very quickly to number of definitions like this. Representation is said to be completely reducible if it is direct sum of irreducible sub-representations. So you have a big representation, you can make it into blocks like this, and each block is irreducible. So in other words, you cannot find a subspace of this n1 dimensional representation which is invariant again. So that means break it up as much as possible. It's like breaking it up into primes, okay, like that. So completely reducible. So irreducible is equal is an analog of prime numbers, and completely reducible is writing as product of prime numbers, something like that. Just another. No, okay, these are just definitions. Of course, equivalent to irreducible representation is also irreducible, because you have two equivalent ones. This is irreducible, this must be irreducible, because if it has proper subspace, which is invariant, image of that is going to be invariant. This is going to be proper because it's an isomorphism. So we have the following very beautiful unitarizability result. So the word unitarizability comes from the following thing. Take a complex representation. One moment. So you have n by n matrices, invertible complex matrices representing the group G. Then what we are saying is that there is a matrix so that conjugate of this group. That means take an element to row of small g. Take an element row of small g inside row of capital G. Then T rho G T inverse is a unitary matrix. So there is a common T which does this job. So in other words, up to change of basis, any complex representation is unitary representation. Any finite dimensional complex representation of finite group is equivalent to a unitary representation. That is what unitary. That's what this is saying. What is the proof? Proof is very easy. You might have seen it in the earlier lectures. I'm not sure. I've not seen whether it was covered earlier by earlier speakers, but I'll mention it. It's very simple. That's why. Idea is always very simple. Sometimes checking things is we have to be careful. That's all. Equivalent to finding an inner product, which is inner. That's what. What is unitary? Unitary simply means preserving inner product, usual inner product. When I say T U and T inverse, conjugate of that group means we have some inner product because it's like change of basis. We take orthonormal basis with respect to this. So the canonical basis is changed into this basis for this by means of a matrix T. That's what this means. So what we want, this condition is simply equivalent to saying there is an inner product on Cn which is left invariant by this group action. That is rho GV, rho GW is VW for every G in G and for all VW, of course. Okay, so that's what we want to know. So this result proof is to say that does there exist such an inner product? And we are talking about finite groups here. So the advantage about finite groups, although they are very complicated, finite groups are much more complicated than infinite groups. Although they are more complicated, there are certain things which are much simpler. For example, you can do averaging and things like that. So for example, here is one. So to get such an invariant inner product, start with the standard one and then simply, standard inner product I called as inner product 0 here, suffix 0. So just average it out or sum it out. Like averaging would mean you divide by order of G here. You can do that also. Scaling this inner product doesn't matter. So this is definitely left invariant inner product, this one, new one that you define. Because when you look at any element of G, say small h, how does rho HV, rho HW look like? By definition, it is rho G, rho HV, rho G, rho HW. That means rho GHV, rho GHW. And when G is running over elements of G, GH is also running over elements of G. So it's the same. So this is as simple as that. So every representation, complex representation of finite group is unitarizable, equivalent to unitary representation. And there is other theorem, which is called Maschke's theorem. Okay, so here complex representation, when it is equivalent to direct sum of irreducible sub-representations. Actually, Maschke's theorem holds more generally. Instead of complex representation, you can even take any field here, except you should avoid fields which have positive characteristic and the characteristic divides the order of the group. Then there is some messing up. Because you see what is happening when you want to average out your divided by order of G. If you have a field of characteristic P dividing order of G, you cannot divide by order of G then. That's the reason. And in fact, it will be false. Okay, it will be false saying that any representation of G to G ln K is completely reducible if characteristic of K divides order of G. But anyway, this Maschke's theorem holds instead of C with any field of characteristic sort of co-prime to order of G. Either characteristic 0 or characteristic P not dividing order of G. Okay. But I stated it for complex simply because you can deduce this from the unitary result. Prove an easy consequence, as I mentioned, of unitary result. What do we want to say here? Take a representation, you want to say direct sum of irreducible. So what does that mean? That means you have a representation, n-dimensional representation. So you have, if it is irreducible, nothing to prove. If it is not irreducible, there is a proper invariant subspace. Take such a subspace W, invariant subspace. Now, advantage is that we have an inner product which is invariant under G by the unitarizability result. So with respect to the inner product, you can look at the orthogonal complement W perp. W perp is again a subspace which is also invariant simply because of this condition. Okay. To say W perp is invariant, what do you have to say? Rho G of small v here is also on W perp. That means rho g of small v is orthogonal to everything in W. So we took rho GV W, and you can push the G here because of invariant inner product. We have taken invariant inner product. So but rho G inverse of W is contained in W, and V is in W perp, so it is 0. What we have shown is that W perp is also an invariant subspace. Now we are in good business because we have subspace, and both are proper subspaces. Smaller dimensions I can go down by dimension. Since it is finite dimension, after some stage you have to stop. So you ended up in a direct sum of irreducible representations. So your representation is direct sum of W and W perp. Okay, so then one cannot but mention this very useful lemma, which comes up in many parts of mathematics. All of you would have faced this somehow or other, whatever subject you are interested in. Schur's lemma will keep coming in. It may come in different guises. It may not stay like this, but the same theme comes up in many ways. But in any case, so Schur's lemma in the traditional way is this: take a group and two irreducible representations, take complex representations. Then if you have a linear map between V1 and V2, which respects the G action, okay. So here V1 G is acting by rho 1 of G, and V2 is acting by root of G. So this condition, any such linear map you consider. Are there such linear maps? Of course, there is zero map is always there. It's always invariant. So, that's not a problem. So Schur's lemma says once these are irreducible, both V1 and V2 are irreducible, then only way such maps can occur is the map is either the zero map or invertible. Okay. And in fact, they are invertible or zero according as to whether rho 1 and rho 2 are equal representations or not. Okay. And suppose you have two equivalent representations, that means V1 and V2 are isomorphic, and there is an isomorphism respecting the G action. So often you choose V1 equal to V2, so that to simplify matters. In other words, you have an irreducible representation on a vector space V, which it's a common name for V1 and V2. Then any such transformation, okay. So from V to V is an irreducible representation. V to V, so V has two irreducible representations. One is called rho 1, other is called rho 2. That means rho 1 from G to GLV, rho 2 from G to GLV, same V. Both are irreducible. Then any such T is going to be a scalar other than 0. Scalar matrix or okay. So this is called Schur's lemma. And the proof is, of course, like one line. If you irreducible simply means there is no proper invariant subspace. Okay. So whenever you have homomorphism, linear transformation like this, of course, we have not naturally certain subspaces. Okay. Subspace meaning kernel of this transformation, image as a transformation. And this condition will tell you both will be invariant subspaces. So there is hardly any choice. Kernel is 0 or full, image is 0 or full, like that. So from that you conclude this. All this will follow through simply by looking at the kernel and image. Okay, but point I'm made this Schur's lemma is, of course, apart from its importance, it has rephrasing. It can be rephrased in different ways also. Here is one rephrasing, which is again very useful. I'll point out how. So rho I and Vi are as above, that is irreducible representations, and T is any linear transformation. Okay, so I'm not taking T is respecting. So let's go back. Here T was taken to be this, and then we conclude T is either 0 or invertible. When T is a linear transformation, respecting the G actions. So here first I'm taking any linear transformation. And how do you make something, any linear transformation to something which respects the action simply by averaging? So in other words, you make this new operator T hash, which is defined like this. Okay, rho 2 G inverse composite T with rho 1 G. So rho 1 G takes V1 to V1, T takes V1 to V2, takes V2 to V2. So this is a V1 to V2. So this transformation, new linear, this is again linear, of course, and the linear transformation is either 0 if rho 1 and rho 2 are not isomorphic representations, and if they are the same representation, then you can actually calculate this. It's a scalar, we know, but suppose you know a representation is a scalar, corresponding T is a scalar. How do you calculate the scalar? By looking at the corresponding trace of the linear transformation. You have lambda, 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 n times lambda, n being the dimension, will be the trace. So trace of T divided by n is the size of it. Okay. So what I'm saying is that you have two irreducible representations, V1 and V2 of a group G, finite group G, then the T hash has these two choices. If rho 1 and rho 2 are not equivalent, then this is 0 map, and they are equal, then T hash is just this scalar. So when you do this, for example, let's apply this. So we have V1 as n1 dimension, V2 as n2 dimension. So let's take any I, fix I less than equal to dimension of V2 and J less than equal to dimension of V1. What am I doing? I'm going to apply this to certain T's, because I started with any T here, right? So what T I'm starting with? The obvious things, we have the elementary matrices, that is, so Eij. So that means Eij, this is the matrix. What is the size of this matrix? It's from V1 to V2, dimension of V2 is N2, this is of N1. So it's an N2 cross N1 matrix. Okay, the T is if you represent T as a matrix, it's an N2 cross N1 matrix. So I'm looking at N2 cross N1 matrix Eij. Eij is N2 cross N1 matrix where only the ijth entry is non-zero, equal to 1. I'm looking at a particular T. Okay, so only one entry is there. Then when you apply this, what do you get? You get the following thing. Of course, there are two things. One is not isomorphic and isomorphic. In the case of not isomorphic, this condition T hash is 0 simply says this in terms of matrices. So it's very convenient. See, this condition gives some nice things also. Okay, let's just say, okay, let me say for when they are equal, then this condition, this is the condition. Okay, then what does it give you? This is what it gives you. Okay, so this is simply because a trace of this matrix is nothing but delta ij. Okay, it is 0 unless I equal to j. Okay, only at ijth position there is a 1. That's what Eij matrix is. So what this gives is, immediately it gives you some so-called first orthogonality relations. I'm sure this must have been discussed earlier. So, but this falls out from the Schur's lemma is what I'm saying. By rephrasing Schur's lemma as we did, Schur's first orthogonality relations follow. What is, remember, chi1 of G by definition is trace of rho 1 G, that function. G going to trace of rho 1 G, that function is chi1. So these conditions simply become equal to 0, and there is an 1 by order G which you can take to that side. So this sum is equal to 0 or order G according to as to whether rho 1 is isomorphic, rho 1 is equal. Okay, this is called first orthogonality relations. In fact, Schur's orthogonality relations, there are two types, first and second. Both are very useful in counting many things. For example, often you have some number of coverings of some certain types of spaces in terms of fundamental groups. You have to count this number of homomorphisms. So in which case, this Schur's orthogonality relations really help in counting. I wanted to include one example, but it becomes too much, so I didn't do that. Schur's second orthogonality is the following. See, remember, first is what? First is representation rho 1 and rho 2 are fixed, irreducible, and both may be equivalent or may not be equivalent, in which case he has these relations. Summation is over small g. Summation is over small g belonging to capital G. Second one is other way, like some kind of think of it like rows and columns. Instead of fixing representations, you fix two elements. Okay, their representations are fixed and you're summing over elements of G. Now fix two elements of G and sum over representations, so to say. So this is the what are you summing over? This is called G hat is a set of all irreducible characters, that is characters of irreducible representations. You sum over that, and this relation holds. Okay. Earlier, what is the first one? Chi1 G, Chi2 G sum was either order of G or 0. Here it is order of the centralizer of G. So G and H are in the same conjugacy class. Of course, number of conjugacy, the cardinality of the conjugacy class is the same for G and H. They are conjugate means, right? They are this. So this is the number of elements in the centralizer of G. So what is the proof of this? Prove this, consider this. So sometimes it's very convenient to use like a matrix character table, because there are as many irreducible characters as the group. So suppose G1, G2, GS are representatives of conjugacy classes. So I'm assuming something here which is a standard fact, which is not, I didn't mention it explicitly here. What is the fact I'm assuming? For a finite group, number of irreducible representations is equal to the number of conjugacy classes. Okay, so if you have representatives for conjugacy classes G1, G2, Gs, there will be again S irreducible representations and corresponding characters are chi1, chi2, ks. Okay, and these are certain numbers, right? If you have complex representations, these are complex numbers. You have complex S cross S matrix. This is called the character table. And using this matrix, we can prove many things, including the sure second orthogonal relations. So correspond, for example, look at diagonal matrix whose entries are the following. Oh, there's a mod missing here. Cardinality of conjugacy class of G1, cardinality of conjugacy class of G2, etc. Cardinality of conjugacy class of GS. Okay, these are numbers, okay? Number of elements. So these cardinalities are positive integers. Okay? They are cardinalities. So by Schur's first orthogonality, we know this, that chi I, chi j bar is going to be either mod G or 0. Because you see, if they're equivalent, then it is mod G. If it is not equivalent, it is 0. And chi I are from different. So the I equal to J, it is mod G. The I is not equal to J because they are inequivalent. Correct. As I said, all these are inequivalent. Chi1, chi2, chi so pairwise inequivalent representation. Because we are assuming that irreducible representations which are up to equivalence are exactly parameterized with the conjugacy classes. The left-hand side can be split according to conjugacy classes, because when you see character is a conjugacy is a class function. Character of H inverse is also character of G, because it's trace of something, right? So because being a class function, you can break up this sum into first look at various conjugacy classes and then sum over them. But over a particular conjugacy class, how many times for a conjugacy class of GR, the same number is going to come this many times. Conjugacy class of GR cardinality times. So this sum is just this sum. In other words, when you look at this, no, what is the ijth entry of xd x transpose bar? It is simply this. Remember, D was what? The diagonal matrix whose entries are conjugacy class, cardinality of conjugacy class of G1, etc., etc. That diagonal matrix. And X is the character table chi I Gj. So when you multiply chi xd x transpose bar, it is simply ijth entry is this. So Schur's first relations we know is simply giving this. So when you rewrite this in the following form. Okay, there is a typo here. Mod G times number of elements of G times identity is xd x transpose. See, this is so once again saying that x times d x transpose bar is equal to some scalar. That means d times, so you can put the x this side. Okay, x times this is a scalar, mean the same scalar is d times this times can change the order. So d times, but when you look at the ijth, it is exactly the relation that we wanted. This is what we get. This is what we get. Okay. So let me not say too much more about the finite group representation theory. So one must mention that very basic fact is that the left regular complex representation. That means what I mentioned earlier also. We have group G of order n. Then you take C power n, or you take a vector space of dimension n, which has whose basis you sort of parameterize by the elements of G. The elements of G are G1, G2, Gn. We call the basis elements E1, E2, En. And G is acting on EI in what way? G is GI and EJ is correspond to GJ. That means what is the basis element correspond to GI, GJ. This is a left regular representation. That means left multiplication of G on itself gives this representation. The fact of the matter is that, basic fact is that the left regular representation contains all the irreducible representations. And in fact, each irreducible representation occurs exactly its dimension number of times. Each occurring dimension number of times here. I said. So in other words, what I'm saying is the following. Okay, this is a typo here, each occurring dimension number of times. Suppose the irreducible representations are say row 1, row 2, row S, and whose dimensions are n1, n2, ns. Okay, so the fact is that what is the dimension of the regular representation? It is the order of G, because I have taken a base vector space whose basis is in bijection with the elements of G. So G has n elements, then left regular representation is n-dimensional representation. So this fact that I'm stating here with the typo here is that n is equal to n1 square plus n2 square plus ns square. So I mentioned this just in passing that it's about finite groups. If you go to more general infinite groups, what happens is, at least for compact group, there is a very beautiful generalization. Just kind of analogously, instead of the in this case, finite group case, you took the vector space of dimension n, which is same thing as taking something called the group algebra over complex numbers of this group G. Instead of group algebra, you take L2 functions on a group G in the case of compact group. So there is a similar statement there. It breaks up into direct sum of each irreducible representation coming exactly dimension number of times. It's called the Peter-Weil theorem. Okay, now one sort of application I want to say, just mention, touch upon a few applications in passing, go to some other things. So this is, often it happens in mathematics that somebody has developed something and people are not aware of that because people in the other community are not looking at what this person has done. And suddenly when they develop it and give a new name, it looks like it has already been done by someone under different guise. So this is a case of that. This is a particular case. Two subgroups of finite group are said to be Gassman. Gassman is a particular mathematician. Gassman equivalent, the permutation representations of the big group on the two coset spaces are equivalent. So what I'm saying is, take a finite group G. You have two subgroups H1 and H2. Okay. Now G has a natural representation. One is, of course, it is acting on itself by left action, left multiplication. Another is when you are given a subgroup H1, look at the cosets of H1 and G, left cosets of H1 and G. You can multiply the left cosets by elements of G, right? So G is acting on the set of left cosets of H1. G is acting on G by H1. G by H1 is a set of left cosets. G is acting on G by H2. These are both some permutation representation. They're permuting them. Okay. Small G1 times H1 is a particular coset. Then G is acting, small G is acting as GG1 H1, that new coset. That new coset may be the same coset or some other coset. So there is a permutation representation. So what we are saying is that subgroups of a finite group are said to be Gassman equivalent if the corresponding representations on the coset spaces are equivalent. Okay. In fact, you can unwind it and say what it means in terms of characters. So looking at the characters, this is equal to statement that as a very concrete statement, each conjugacy class in the full group G intersects both these subgroups in the same number of elements, because character counts such things. So actually the action of a group G on the left cosets G by H, left coset space G by H, is nothing but something. Sometimes it's also called the induced action of the trivial representation of H to inducing it to G. This is equivalent to that. Okay. In fact, left regular representation of G on itself is the induced representation from the identity group to the full group. There is a notion of induction, inducing the representation. In any case, so when you look at this fact, character can be easily calculated and equivalent. So G on G by H1 and G by H2 are equivalent if and only if take any conjugacy class of G, number of elements inside H1 in that conjugacy class and number of elements inside H2, they are same. This is equivalent to this being representation being equivalent. So this property was, as I said, first studied by Gassman long back. Many people are unaware of that. So mention in passing that this in the 1980s, I think 84 or something, Sunada, some path-breaking, beautiful paper he wrote. So this is about totally different subject where you want to construct certain manifolds which have Riemann manifolds which are isometric. Sorry, they are not isometric, but they are the same spectrum of the Laplacian mapping, whatever that is. For people who don't work in the subject, there is a Laplacian mapping, so it has eigenvalues and so on. That's a spectrum it forms, infinitely many are there. So they might have same spectrum, but they may not be isometric. So this is sometimes very used in a very beautiful language called, because spectrum of a Laplacian is like harmonics. So it's like sound you can hear, and isometry is the shape. So it's like we cannot hear the shape of a drum. In other words, two differently shaped drums might have the same acoustics. Okay. So this theme has been developed in many ways. So Sonada's paper, it considered many such manifolds, and it just simply depended on producing many examples of finite groups and subgroups which are Gassman equivalent. Okay, and this plays a role in many other roles. Maybe I mentioned this also here. For example, number theory, there is given a number field extension, finite extension of rational numbers, a number field K. We attach to it some nice analytic function called, analytically defined function called Dedekind zeta function of that number field. So you have the rational numbers itself, you have this called Riemann zeta function. So for any number field, you have corresponding zeta function called Dedekind zeta function. So natural question would be, oh, we are attaching it naturally. So does Dedekind zeta function determine the number field? Two number fields, can they have same Dedekind zeta function without the number fields being isomorphic, same? And in fact, they can be. And in fact, exactly the same construction gives you examples of such number fields, the same Dedekind zeta function. Okay, I'll go up to one more example, one more different type of example I'll mention. Mouth is getting dry today. So there are so many things about linear groups that some of them are very pretty also, and some of them are related, and it takes a lot of time to talk about. Maybe we should have full summer school about linear groups only. Anyway, so let's look at an abstract group G, and we suppose the group is finitely generated. Okay, so finitely generated groups will have only finitely many subgroups of any given index, right? Because what happens, how do you get a subgroup of finite index given index n? H is a subgroup of index n, then the set of left cosets G by H on which G is acting. So there are only finitely many homomorphisms from G to Sn. If you have finitely generated group G, for any n, G to Sn, there are finitely many homomorphisms, because generators, whatever they go to, will determine this for a given n. Okay, so that means given any finitely generated group, there are only finitely many subgroups of any given index. So then you can talk about this number. So this number is number of subgroups of index n, or number of subgroups of index at the most n. Suppose there is a fixed constant, okay, bounded constant, so that number of subgroups of index at the most n is polynomial. There is a polynomial bound for it. Okay, number of subgroups of index at the most n is not growing like n power n or e power n or something like that, 2 power n. It's going only as n power something, fixed number. Then they say the group has a polynomial subgroup. So because one studies these properties and coming from some other part of mathematics, but then you would like to classify them and so on. Then automatically linear groups come in. This question is just for abstract groups. So we might say, okay, I'm not interested in abstract groups. But then you see something like this. This is a very beautiful theorem by Lubotsky, Mann, and Segal. Okay, so finitely generated, residually finite. I'll talk about residually finite also. What is residually finite? That's this element, this phrase means the following. Okay, so G has many, so think of it informally as G has many finite quotients. There are many finite quotient groups of G. It's not guaranteed. Once a group is infinite, it does not mean it has finite quotient groups, many of them or something. So what does many mean? Many means the following. If you like, so if a finite quotient means what? You have a normal subgroup of finite index, right? The quotient by, when you take the quotient group by that, you get a finite group, right? So we want many normal subgroups of finite index. What does many mean here? If you have two different elements, we should be able to find two normal subgroups of finite index, one containing this, not containing the other. Like that. In other words, take any element which is not the identity element, there is a normal subgroup of finite index to which it does not belong. It avoids. So it survives in the finite quotient. Any non-trivial element of the group survives in a finite quotient. That's what is meant by many finite quotients. Okay, so such a group is called residually finite. The definition of residually finite is that. Okay, residually finite definition is any non-trivial element of G survives in a finite quotient of G. Survives means goes injectively into. It's not in the kernel of. Okay, so suppose you take and why I'm taking this condition is that if you have okay, so you can reduce the problem, this kind of problems about characterizing this to residually finite groups. You can take intersection of all the normal subgroups of finite index and so on. Anyway, so take a finitely generated residually finite group. When does it have polynomial subgroup growth? That is, number of subgroups of index at the most n grows polynomially. They showed that if and only if group is virtually solvable. I yesterday talked about in tutorial. Virtually solvable means there is solvable subgroup of finite index and of finite rank. Finite rank simply means that okay, any finitely generated subgroup is generated by some d number of elements. D is bounded. I mean, your group may be finitely generated, but when you go to various subgroups of finite index and so on, number of generators might go unbounded. Then it's a infinite rank. So finite rank means there is a bound on the number of generators of any finitely generated subgroup. Okay, anyway, so this is an if and only statement, and equivalently, these things happen. So in fact, they're all related very much. You don't just independently prove this and prove this. You prove the first statement by proving the second one. If and only if G is virtually solvable and is linear over Q. Okay, so it is a linear representation over Q. That means it is a faithful linear representation over rational numbers as a group of invertible matrices over Q. So I must tell you, I didn't, in this statement, so much is contained, you may not realize unless you know this theorem. Namely, for example, while proving this, they proved an analog of the Hilbert's problem. Hilbert's problem, yesterday I mentioned in tutorial, is that when is a topological group a Lie group? When it has no small subgroups and so on. So that is the Hilbert's problem. There is a, if you have analog of that for not usual Lie groups, but for so-called periodic Lie groups. Okay, I'm not even introduced periodic, so just take it as a phrase. So just like real numbers, complex numbers, they're periodic numbers. So there is an analog of which kind of P groups or pro-P groups are going to be periodic Lie groups. That's the analog of Hilbert problem, and they solve that. And that is how they get this theorem. Okay, but nevertheless, see, so something is linear and virtually solvable if and only if this growth is like that. So these two are totally seem to be unrelated. So it sort of comes naturally. Okay, now, okay, I have time. If a finitely generated group is n torsion, that means every element satisfies G power n equal to identity. Is the group finite? So Bernstein asked this question. Okay. So if there is an n such that every element satisfies G power n equal to identity, and the group is finitely generated. If it is not finitely generated, obviously it need not be finite, because you see, you can just take infinite product of Z2 cross Z2 cross Z2 like that, right? So it's not finitely generated. So if a finitely generated group has every element of order bounded by something, is the group itself finite? It's called restricted Bernstein problem. And in fact, you need not even put this restriction. Suppose you can ask the more general question, which is that, is there a, I mean, every element has a finite order, the group is finitely generated, is the group finite? Okay. And of course, the answer is negative in general. That the group could be infinite actually. But in the case of matrix groups, this has a positive solution. Okay. For linear groups, answer is yes. So naturally, this comes out of something called the Bernstein lemma. So I'll recall this comes up in many places. It is even true that any finitely generated linear group with all elements of finite order must be finite. So general one, not the restricted one. Here I said every element has order dividing n. Okay, I not put this condition. Still, the group is finite. What I'm saying is, if for a linear group which finitely generated with all elements of finite order, there must be some n first of all, so that every order is divisor of n, and then finiteness. So you're first bounding n and then solving the restricted Bernstein problem positively for linear groups. Okay, every finitely generated linear group with all elements of finite order must be finite, and it is far from true in general groups, general abstract groups, non-linear groups. Very, very crazy examples will be there also. Okay, so to see this, recall that a matrix or an algebraic closed field, which we call it as unipotent. Okay, you know the matrices are called nilpotent, we know that. Unipotent is that it is just identity plus nilpotent. Okay, so all the eigenvalues are 1. And we know that such a thing you can upper triangularize with the triangle entry is 1. Okay, I'm over complex numbers. So let K be any field, and Bernstein's lemma says this. Take a subgroup such that set of traces is finite. Okay, take the set of traces. We are not asking for any more condition right now. So subgroup of JLN, it could be an infinite group for all you know, but we want to say under certain conditions it must be finite. The condition I am putting is set of traces is finite of some cardinality R. And one more assumption. So I can, okay, there are versions of this Bernstein lemma. One version will have this one, another version will something else. So I'm taking this version. No element of non-trivial element of G is unipotent. The reason I'm taking this is I'm assuming K to be any field. If I assume to be K to be of characteristic 0, that is like complex numbers and so on, I don't need this condition. So it's like this. So you'll see why immediately when I tell you an example. Suppose you take the group, you take a field K of characteristic P. You want to say FP, FP bar or something like that. You take the group 1, X, 0, 1. X is varying over the field K. When you take pth power of this, it is just 1, 0, 0. So pth power is identity. Okay. So there are so many elements whose P order P is of order P. These unipotent elements give that. So you cannot avoid that. So in the characteristic P case, you want to avoid it. So either avoid the characteristic, say the characteristic 0 or something, or you say the characteristic is positive, but the element is not unipotent. Okay, this is the version we take. Then G must be finite. Set of traces is finite and G has no unipotent matrices. Then G must be finite of this cardinality, R power n square. So I'll give the proof of this. Maybe if I don't have time, I'll prove it during tutorial, but maybe we have time. So first of all, let's note a very interesting corollary of that. Let K be any field and n is a natural number, which is not a multiple of the characteristic. Okay. So for example, characteristic 0, no condition on n. And this is capital N. Okay. And look at a subgroup of GL n K, n being small n. Okay, it's different. And it's an n torsion group. That means nth power of any matrix is identity. Then G must be again finite. So no unipotent condition is put here, but that will come automatically from here. Anyway, so what we are saying is that you take a subgroup of GLN, that every element is of order n, and n is sort of good with respect to the characteristic of K. So which means no relation when characteristic is 0, no condition. But when characteristic is P should not divide n. Now in that case, G must be finite. Okay, so this is the one-side problem. Note that this may be false if characteristic divides n. It does, it can be false actually. It's not just we are avoiding for convenience. It's like Mashke's theorem I mentioned. It's false actually. So let's look at the lemma of one side. So first, let's prove the corollary. Okay, corollary is that a subgroup of JL and K. Every matrix is of order capital N, or not order, but every matrix power capital N is identity. Okay, order of that matrix will divide capital. Then we want to say G must be finite automatically. Okay, somewhere we'll use this characteristic condition. Basically, to use the characteristic condition to show that there are no elements which are unipotent. And then you'll apply Bernstein lemma. We'll be applying Bernstein lemma to prove this Bernstein kind of problem. So I should have not have put the whole thing in a single page. Okay. Without loss of generality, assume that K is algebraically closed, because your subgroup of GL and K can also think of subgroup of GLN of K bar being an algebraic closure. So neither the hypotheses are affected nor what we conclude is affected. So now what we want to know is that Bernstein lemma can be applied. So we are going to look at the set of traces. Now look at the vector space, subspace of M and K generated by G. So G is subgroup of JL and K, remember? Because we cannot, in a group, we can only multiply, matrices can be multiplied, but JL and K is fortunately sitting inside M and K. So we can add elements, can add matrices, so we can add the elements of G. So you are looking at the vector space generated by G inside this. So it's finite. So okay. So it's vector space generated by G. This is a finite dimensional vector space. M and K is n square dimensional vector space. So this has some dimension, n square, at the most n square. Actually, if the characteristic 0, you can, and the action of G is irreducible, you can, on K bar is irreducible, then we can actually show that D is n square. But we don't need anything about T. We just want that, look at the vector space generated by elements of G inside MNK. There's some dimension which is less than or equal to n square. Okay, some dimension D, let's say. So we have element G1, G2, GD, elements of G which give a basis of this vector space. Now we are assuming this corollary assumption is that every element satisfies G power n is entity. So eigenvalues are of course going to be nth roots of unity. So what will be the trace? Trace will have sum of eigenvalues. So each eigenvalue has n possibilities, and the matrix of size n cross n. So each diagonal entry has each eigenvalue has capital N possibilities, and there are small n eigenvalues. So there are at the most n power n possibilities for the trace. Okay, so we have the Burnett lemma condition that trace of any matrix, the set of traces has finite cardinality. What I called as R in that lemma. So this is R n power n. None to apply. Okay, let's go back to apply this lemma. Not only traces should be finite set, we should also assume have that no element other than the identity is unipotent. So for that, suppose if possible, here is the unipotent element G, non-identity element. So what you can do is you can conjugate this given matrix by some GLNK matrix, make it upper triangular. Okay, I assumed here K is algebraically closed in the beginning itself. So that's how you can do it. So you can make it upper triangular with all diagonal entries 1. Okay. So I want to say it is impossible. I want to get a contradiction to it being unipotent. If it is unipotent, you can do this upper triangular with diagonal entries 1. Once you do this, look at the sort of shortest proof will be to say that look at an entry Gij which is not equal to 0 with J minus I smallest possible. The difference J minus I. Remember, it's upper triangular. Okay. Now looking at the ijth entry of this, you get this condition. Here is where characteristic plays a role. Okay, the ijth entry will get this condition. Oh, somehow, yeah, it's visible here. This is a contradiction since characteristic does not divide, and Gij is not 0, but n times Jij is. So in other words, your capital G cannot contain non-trivial unipotent matrices, and then you can apply this. So it will tell you that whatever trace cardinality is, say R, are bound for the traces is R, at least at the most R number of elements in the trace set. Then R power n square is the bound for this, and that's all. We said trace set has at the most n power n elements, right? Because eigenvalues are nth roots of unity. So there are capital N possibilities for each eigenvalue, and there are n eigenvalues. So at the most n power n possibilities, that is your R. So R power n square is n power n cubed. Because this is a very big bound. It's not practically, it's much smaller. So we really proved this corollary, beautiful corollary, that so just think of this, instead of complications, just think of simply this. Take a field of characteristic 0. Suppose you have a subgroup of GL and K in which every element is of some order dividing capital N, then the group must be finite. So Burnett problem has a positive solution. Okay, so what is the Burnett lemma go? Burnett lemma is very easy to see again. Yeah. So as before, let's look at G1, G2, GDB elements which form a basis for the vector space spanned by the elements of G. Now what we do is we just map the following thing. So we want to know G is finite and so on, right? Suppose you are claiming G is finite, you should be able to say, oh, order of G is at the most this. So you want to bound G, you want to map G to some set which is finite and in one way. So this traces give a very natural way of doing it, is what I'm saying. So for every G in G, look at the D tuple like this. G1, G2, GD are the generators of this vector space. So look at trace G1G, trace G2G, trace GD. Now I'm saying given two elements G and H, the corresponding tuples are different. The same tuple are associated to elements X, Y, in G. Then what do you have this condition? Trace of Gi times X minus Y is 0. Okay. What does that condition mean? First of all, you notice that this simple what should I say, identity, I minus x inverse y power k times x inverse is some summation lambda I gi, because gi is basis of the corresponding vector space. Therefore, multiplying, so there are so many equations here, d equations, multiplying the dth equation, trace of gi times x minus y by lambda and adding, then you get here trace of this is 0. So this holds for all k. Okay, we have matrix so that trace of this power k is 0. That means this must be nilpotent matrix. That means your matrix x inverse y is unipotent. You know that there are no unipotent matrices other than the identity matrix. Okay, so that's how we got this. Because in Bernstein's lemma, that version that we have stated, we are assuming there are no unipotent matrices other than identity inside capital G. So x inverse y is a unipotent matrix, so it had better be the identity matrix, which means x is y. That means there is a 1, 1. So we have mapped your group to this D tuples like this. Each of them has how many possibilities? R possibilities. That's what you assumed in the lemma, R, small r possibilities. And so that means how many elements capital your group G can have at the most R power D. And you know, D is just basis of vector subspace of MNK. So D is at the most n square. So that means R power n square is what you get. That is what we have set it. Okay, there are some other similar. So I mentioned, because our linear groups are very special, some very nice properties hold, which don't hold for general groups. In fact, they can go very wrong for general groups. That is why I mentioned this is a striking one. Bernstein problem is 1. Okay, I thought I had whatever I explained is written here. Association is 1 to 1. Trace can take at the most R value. So we have at the most R power D here, which means R power S. That is Bernstein's lemma. By the way, the name Bernstein's lemma is given to several lemmas. Sometimes they are not even due to Bernstein, because Bernstein has a beautiful book, and he might recall, especially there is one called one due to Cauchy and Frobenius and so on, different versions, which is now known as Bernstein lemma. And a lot of people are now writing to say that should correct this, called Cauchy-Frobenius lemma or something. So, in fact, one of the group theorists by name Peter Neumann, he wrote a paper called the not Bernstein lemma on this. So, in fact, I also followed suit and wrote a paper where I call it an application of not Bernstein lemma. Anyway, so names sometimes wrongly given, they stay. It's okay. It's as long as you know some history, it's good. For example, Pell equation, nothing to do with Pell. So Bernstein also proved the following result. Only one result I'll mention like this, using the same ideas. A subgroup of is finite, if and only if it has finite many conjugacy classes. It's really beautiful. See, such a neat looking result. And it's proved the same set of ideas. Okay. Number of conjugacy classes is finite, if and only if the group is finite. These things are not true in general. For linear groups, they are true. So here is the outline of proof. Maybe we'll see. So the only if part, what is meant by only if part? Sorry. If it has, so if the group is finite, it has finitely many conjugacy classes, obvious. So only if part is obvious. So we prove the if part. So assume the group has finitely many conjugacy classes. As before, the group is inside GLN K, you can put inside GLN K bar. So you can assume that already the field is algebraically closed. This assumption implies the set is trace set is finite subset, because number of conjugacy classes is finite. On a conjugacy class, the value is the same. Trace value is the same. So that is how this conjugacy class plays a role here in this proof. The trace set has a finite subset. So first thing is here I had to be, because you are going to use another version of Bernstein lemma, so I don't want to state it like that. That is why I included it. I included the following thing here. So if the action of G on K power n, G is subgroup of GL and K, so it's acting on K power n, we know action may or may not be irreducible. If the action is irreducible, then there is a vector space basis of n square elements. Okay, this is another version of Bernstein lemma. Okay, so sometimes it comes under what's called Wedderburn theory, something. Doesn't matter. The fact is, if G is acting irreducibly on a K power n, K is an algebraically closed field, then a basis of Mn key has n square elements coming from G, full n square, okay, coming from. So in other words, G itself gives a basis. You don't need to have basis of Mnk, which are coming. G is contained in Mnk, of course, but why should only elements of G give a basis? So this is only the irreducible action. So this I am assuming. Then the map Mnk to Kn square, which is given by the trace any, just like previously we had taken G going to trace G1. Similarly, like this from whole of Mnk I am taking this time. Earlier I was taking from G. So M2, so M goes to trace Mg1, etc. This tuple, n square tuple. Once again, this being a basis, this is 1, 1. So this is how many choices? You have some R choices. Then n square tuple it is, so R core n square. Okay, so we got this provided the action is irreducible. But if it is not irreducible, what happens? That's why I'm assuming that the action is not irreducible. That means what happens? This means the following thing. See, when the action of G on K power n is not irreducible, there is a proper subspace which is invariant. So let's say some subspace of dimension M is invariant. So you what should I say? Extend the basis of that space to the full space K power n. Okay, or subspace W of dimension M, which is left invariant by the group. That means with, and I extend that to a basis of K power n. With respect to that basis, how do the matrices on G look like? With respect to the new, because W is taken to itself, W is the subspace of dimension M. This is an M cross M matrix. Oh, I call it N1 cross N. So it's an N1 cross N1 matrix here, and 0 below because W is taken to itself. Whereas when you extend the basis, there is no guarantee that this is taken to. So there's no guarantee that there is a 0 here. That's what we want to really do. Okay, so your N becomes sum of N1 plus N2, and N1 cross N1 block here, 0 here. Now let's see what happens. So we look at this set of elements, small g1 arising in this manner, small g1, small g2. These are groups, of course, and we are going to apply induction because when the action is irreducible, it's finite. We have already shown. That's what we are going to apply as induction. So, but by induction, we will assume capital G1 and capital G2 are finite. But then look at the homomorphism from the group G. G is consisting of such blocks like this. N1 cross N1 block, 0 below, and whatever, something here. So you send it to the H part here. So you send this to only the H part, which means identity here. So kernel of that is precisely this G1 cross, which is a, sorry, you take the other way. What I mean is take from group to this finite group. And kernel consists of these things, right? When you map it to G1, G2, what is the kernel? Only identity H0I. So this is the kernel. Since this is a finite group, we are assuming by induction hypothesis. That means H is a finite index. So each G has only finite many G conjugates. Okay. Because this group is abelian, you see. Okay. Because this is finite index, hence it must be finite. So that is how we apply induction. So we have proved this nice result. A subgroup of GL and K is finite if and only if it has finite many conjugacy classes. Striking result. So I think go to the one more fact I'll mention before go to the last topic here. So you might wonder, okay, given some group, let's say a finitely generated group, how can you put it inside a matrix group? How are you assured that there is a faithful, that is 1-1 representation? Faithful simply means 1-1 homomorphism to GL and C for some n. How are you assured of that? Or whenever you are assured of this? Can you give a condition on the group? And indeed, this was given. This was given by Alex Lubotsky. Remember, Lubotsky, Mann, Segal figured in the earlier one, polynomial subgroup growth, same Lubotsky. So, to state the criterion, one small notion I will recall, one small definition. For any prime number P, on a finitely generated group G, we call a P congruent structure. Okay, P congruent structure simply means we have a decreasing chain of normal subgroups N1, N2, etc. G contains N1, contains N2, contains N3, this chain like that. Okay. Each Ni is normal in the full group G, and they are really getting decreasing in such a way that intersection has nothing except the identity element. And not only that, at the first level and the ith level, N1 by Ni is a finite group of P power order. It's a finite group of P power order. The group G itself could be infinite right now. N1, N2, here's some chain like that. N1 by Ni is a finite group. And not only that, each Ni by Nj is generated by D is the number of generators for any subgroup like that, at the most C elements. So suppose you have such a chain of normal subgroups in a group G, we call that as a P congruent structure. The P is coming from this P. Okay, these ideas are again related to that theorem I stated earlier about Hilbert problem. When is a how do you have a Hilbert problem for periodic groups? Anyway, so this definition is there. One of the examples, so earlier we had discussed yesterday, I think, that SL and Z, look at the kernel from SL and Z to SL and Z mod P, it is torsion free. Right? That is so the notation for the SL and Z mod P, the kernel of that, suppose you call it as gamma of P. Similarly, you can call gamma of P power I as the kernel of the homomorphism from SLN of Z to SLN of Z mod P power I Z. Only thing you remember is SLN of Z mod P power I Z simply means Z mod P power I Z is it's not a field, some ring. It's a finite ring like that. But nevertheless, you can consider n by n matrices with coefficients entries from that ring, whose determinant is 1. Right? So there is a group homomorphism from SLNZ to SLNZ mod P power I, which you can easily show to be onto, and its kernel is be gamma P power I. So these are sometimes called congruence conditions because the kernel consists of things, matrices that this is congruent to the identity matrix modulo P power I. When you subtract the identity matrix from the matrix in this kernel, all the entries are P power I times something. That's why it's called a congruence. So this is a natural example of P congruent structure on SL and Z. We have defined a general group, what is meant by P congruent structure, and I'm giving a natural example. So in some sense, this is crystallized out of such concrete example. So this is the abstract definition. Like somebody is talking, no? Anybody has a question? Okay. So what is criterion for a group to be linear is the following. Take any finitely generated group. The following conditions are all equivalent. So being linear simply means you have a faithful representation, complex finite dimensional faithful representation. Faithful simply means the homomorphism from G to GLNC is 1, 1. Okay. Otherwise, you can always have representation. Everything can be sent to identity like that, right? Should be 1, 1. Okay. Nothing should be lost. So its faithful representation exists if and only if it has a P congruent structure for some prime P. But once it has for some prime P, it is forced to have P congruent structure for all but finitely many primes. This is the kind of theme which comes up in this kind of mathematics. If you say for some prime, then it follows for almost every prime. Okay, the ideas are so connected like that. This is a way to, so you're forced to check. You need to check only one, but then it contains. These are all equivalent. Because suppose I don't state the part 1. Suppose I say finitely generated group 2 and 3 are equivalent. That means it has P congruent structure for some prime P, it has P congruent structure for infinitely many, or all but finitely many. Already it's striking. You don't know how to approach it then. But the point is, it drops out of the kind of ideas. So of course, I'm not going to this proof. My last topic I want to say is a little bit about symmetry groups of solids, where linear groups again play a role. I'll sort of quickly pass through this and finish off. We have how much time? Okay, 8 minutes are there, but I'll finish before that. So group of rotations of a cube, which lead, so the cube doesn't change, okay? So I have put in a single page. So think of this cube in space. So various rotations which are there, which leave it invariant, doesn't change it. It's a rigid body. So 90-degree clockwise or anti-clockwise rotations about the axis joining the centers of the opposite faces. Okay, faces are there. So there are six faces like that. So there are 6 such rotations. Then 180-degree rotations about each of the above axis. So fully 180 degrees. Again, after doing that, cube looks the same. Then there is 120 degrees clockwise or anti-clockwise rotation about axis joining opposite vertices. This can imagine. Okay, when you do this 120, then it looks the same. 180-degree rotation about the axis joining the midpoints of the opposite edges. Okay, opposite edges. There are again 6 because there are 6. And then, of course, identity is there. So now counting such things is quite difficult usually. If you have more complicated figures, for cube, this is 1. So what is this? So let me give some example first. Cyclic group can be regarded as subgroup of permutation of the vertices of a regular n-con. Take a regular n-con plane like a regular polygon of n sides. Then cyclic group just moves one vertex to the next one, next one, next one. Rotation by e power 2 pi I by n. Think of it like that. Or if you want to think of it as permutation of the vertices, then 1 goes to 2, 2 goes to 3, 3 goes to 4, n goes to 1. So you are just rotated by e power 2 pi I by n. That is the action of Cn on this. Leaving the regular polygon invariant. It looks, effect is again the same. The same, it does not change position. So it's if you want to view it as a permutation group, it's generated by the n cycle. So cyclic group generated by n cycle. Remember, n is any general thing. If you take square of that, the cube of that, it may not be n cycle. If you have 1, 2, 3, 4, this is 4 cycle, what is the square? Think of those things. Similarly, you have the dihedral group, where again you have a regular polygon of n side. Now it depends on when it is odd or even. So when you have a pentagon, for example, then you have this from one of the vertices to the midpoint of the opposite side. You look at the rotations about that, reflections about that. Then it's again invariant. If it is hexagon or even-sided things, and of course you have this. So in other words, depending on n is even or odd, you can just describe this dihedral group given by n rotations. What are the axes you can define depending on odd or even? Axis might be from a vertex to the midpoint of the opposite side or between vertices only. Just like midpoint or the sides, midpoint of one side and the opposite side. Okay, so we can just again view it as a permutation group also. If you just name the vertices, you can think of it as permutation group. So this is one way of looking at all these groups as permutation groups. As I mentioned here, subgroup of Sn. N rotations correspond to the powers of sigma, and the group is the subgroup this. So this is a familiar form of writing the dihedral group. But I am writing here also as permutations. 1, 2 to n, this n cycle, okay, that is one thing, rotating all this vertices, and then reflections like this. So together, so they don't commute. Rotation and reflection don't commute. That is why this become this kind of thing, sigma, tau, sigma. So there are 2n elements like it. Okay. Identity sigma power n minus 1. This is a group of order n, generated by the n cyclic group, and to each of them the coset tau times tau times tau. And if you take sigma times tau, then it can be written in terms of this. Sigma times tau will be tau times sigma power n minus 1, etc. Anyway, so tau you can explicitly write in terms of the vertices, how the vertices are permitted. Whatever you call. So if you say 1 is okay. Anyway, 2 and n are interchanged, 3 and n minus 1 are interchanged. You can imagine it's reflection about a particular axis. Also mentioned, for example, Rubik cube group is a subgroup of. So we have actually 48 parameters there. So permutation group on 48 symbols, you can imagine how big it is. 48 factor is a humongous number, but it is simply generated by 6 transformations. That is why people are able to solve Rubik cubes very quickly. Of course, they intuitively see the shape, but because nevertheless it is generated by some 6 transformations, they can do it very quickly. And so transformations are basically those of the front, back, upper, lower, right, and left faces by certain quarter rotations. But the group is very large actually. Even though the number of generators is just this, group has this order approximately, something like this. Okay, it's very interesting that so one can of course give a theory and easily solve the Rubik cube, but in all these things, there is a geometric intuition which you can see. Okay, you do it much quicker. So the book way of doing it is ensuring that you have a solution. But often they're not, nobody is going to follow that rule. Okay, these are the Platonic solids, as you know, very bad picture. Okay, tetrahedron, octahedron, cube, and icosahedron. This is 5 Platonic solids. So, what are the symmetries of these solids? Determination of finite subgroups of the group O3 or SO3 plays an all-important role in proving that there are. So, how do you show that these are the only 5 Platonic solids, the cube missing? So that problem is equivalent to finding subgroups of SO3. Or actually, I should say O3. Okay, symmetry group of a 3-dimensional figure is a set of all distance-preserving maps or isometries of R3, and we know that is nothing but O3. And okay, and once origin is taken to origin, it's O3. To make this more concrete, we view each Platonic solid centered as what centered the origin. So an isometry which sends a solid to itself then must fix the origin. Okay, that's what it says. Symmetry of the solid means the center should be fixed there. That means it's an isometry fixing the origin. Then we are in good shape because we know once it fixes the origin, it is nothing but linear map, and the linear map is given by an orthogonal matrix. Matrix is given by A trans and 3 by 3 orthogonal matrix. So for each of the solids, we have to find out what are the corresponding symmetry groups, or even other way, find all the finite subgroups of O3 and what are the solids corresponding to them. Both ways it will lead to the fact that there are only 5 Platonic solids. Okay, so isomorph is a subgroup of the orthogonal group. Elements of these are either rotations or reflections across the plane. Okay, this is very special about depending on whether the matrix is determined 1 or minus 1. Okay, of course, just the rotations if we take, this is of index 2, this is SO3. Symmetry group of Platonic solid viewed as a subgroup of this thing. Then look at the subgroup of rotations, that is only those in SO3. We note that if it is x going to minus x, then it's a reflection and it's an element in the center of O3R, and then O3 is isomorphic to its subgroup of index 2 cross this central element. So these are all, of course, easy group theoretic facts. Okay, so this is of index 2 mentioned. So in particular, G is, of course, Platonic symmetry group, a subgroup of O3. So G is to R is also at the most 2 because it's less than or equal to this. Okay, because G intersecting SO3 is your R. Okay, G is to G intersecting SO3 is less than or equal to O3 is to SO3. So element Z is a symmetry of all the Platonic solids. The central one, this one, except for the tetrahedron, and there are reflections which preserve the tetrahedron. Therefore, so as I said, is less than or equal to, but in most cases it is 2. But for the tetrahedron, it is 1. So for the 4 largest solids, it's actually 2. That means rotation cross this reflection. So in other words, in a table, if I put it like this, for tetrahedron, the group of rotations is A4. The full symmetry group is S4. Other groups, otherwise, rotation groups are these, and then cross this reflection, XZ going to minus Z. Okay, for the cube and the octahedron, dodecahedron, icosahedron. Okay, I think I should stop here because time is up. Thank you. So if you have any quick question, you can ask me. Otherwise, you'll meet during tutorial 2:30. Okay.
Thank you, sir.
Thank you very much.